I'd like to present Evan Zabowski. He's the Senior Technical Advisor with Test Oil. He's been with us for a number of years, and he's incredibly knowledgeable in the field. So I'll hand it over to him so he can go ahead and educate us on synthetic oils.
All right, thank you, Heather. So yes, today's webinar is about synthetic oils. As you can see, I have called it an overview because we're not going to get into that much detail because most people don't need to know all the details, but we do need to know a little bit about synthetics. So my first and foremost warning to you all is that don't worry, it's not a chemistry lesson. We won't get into too much of the chemistry, but we do need to understand chemistry a little bit so that you can understand how different a synthetic really is, or probably more likely isn't. So with that, let's get started with a couple of definitions. So my first definition, to make sure we're all on the same page, is just what a hydrocarbon is. Simply put, it's a molecule that has hydrogens and carbons. That's it. That's as much as we need to understand this. Now, when we start talking about oils, we refer to them usually as hydrocarbons because many of them are hydrocarbon based. But the big question is, where do they come from? And as you can read here, I say they occur naturally. That's the key thing here. They're natural molecules in the world. And most of where we get these is usually crude oil. If not, it could be from natural gas or some other naturally occurring deposits like coal. But what we need to do is we need to separate out the parts we want from the parts we don't want. And the other definition I just want to start us off with is fractional distillation. Big mouthful, but simply put, every hydrocarbon molecule, as it gains another carbon and gets bigger, is the sort of key thing I'm going for here, the boiling point of that particular molecule gets higher. So if you're familiar with distillation, one of the more common forms that some of us might know a little bit about is moonshine. When you make moonshine, you end up with water and alcohol. And you don't want the water, but you do want the alcohol. Now, alcohol has a lower boiling point than water. So if we heat the mixture up to a boiling point above the boiling point of alcohol, but below the boiling point of water, what we end up with is an ability to separate out the alcohol from the water, because the alcohol will boil, the water will not. The alcohol will turn into vapor. We can collect and condense the vapor and separate it out. When it comes to hydrocarbons, as I said, the bigger the molecule, the higher the boiling point. We can separate out the different molecules just by heating it up to different temperatures. So the big, most complicated slide you're probably going to see is this one. And this just gives us an overview of how that main step occurs. And this is one of the common ways we have of making oils from crude oil. As you can see in the middle here, we have these different fractions, as we call them. And as we go through these, you can see the number of carbons gets higher and higher, and therefore the boiling points also get higher and higher. And so with all these stages inside of a fractional distillation column, we heat the oils up, we separate out the molecules. And here's how I'm going to try and simplify all this so it's not a chemistry lesson, but you're on the same page I am. Now, this may be a bit of an oversimplification, but this is, I think, what we need to understand. If you look at those top categories, gases, naphthas, kerosenes, and gas oils, I'm going to refer to anything in that hydrocarbon molecule size as small. And if you look at near the bottom here and look at the hydrocarbon sizes for fuel oil and asphalt, I'm going to call those ones large. The only one I haven't addressed is the one that we use for lubricants, and I'm going to call that one medium. So we have small, medium, and large molecule sizes when it comes to all the molecules that could appear in crude oil. So to make oils, we need to decide which ones we want to use. And predominantly for lubricants, we're using these medium-sized ones. And just to give you an idea how uncommon the medium-sized molecules are, this is a sort of a cross-section of all the products that we get from crude oil. And you can see the biggest slices of the pie here, the first three in particular, are all fuels. Those are all small molecule sizes. And then you go through some of the other ones and they range back and forth between small and large. But when you get to that second last slice as you go around the pie there, you see this tiny, tiny little segment that makes up lubricants. These are the medium-sized molecules that we want, and there's not that many of them. So funnily enough, as I say here, we call these companies oil companies, but they don't really make a lot of oil. They just use a lot of oil. And from that oil, they make a plethora of products. Lubricants is just a small, small portion of it. So to keep us on a simplified approach, let's just think of it this way. If you ask the average person on the street, how do you think we make oil? Most people actually have a reasonable understanding of mineral oils. They know a mineral oil, step one starts by getting crude oil out of the ground. Now, that could be drilled on land, over the ocean, could arrive from mines. There's a lot of different ways we can do it, but they know somehow we get crude oil out of the ground. Then they know it goes to a refinery. They don't necessarily know what a refinery does, but they know it does purify it to some point. Then that refined product gets some additives put in it, because again, most people know that there's additives in oil. And last but not least, we package it, and whether it's in totes, drums, barrels, whatever it happens to be in. But those are the 4 key steps. And why I put this presentation together is because a lot of people have misconceptions about synthetic oils. Because if you'd ask the same group of people who could come up with a list like this of the main steps involved in making mineral oil, and said, how do you make a synthetic oil? They start throwing around terms like man-made and artificial and chemical synthesis, and they really don't necessarily have a strong understanding of this. And in fact, they might just think it's practically magic. So let's try and simplify it. Keeping in line with what we have here, to make a synthetic oil, step one, not a whole lot different. We take crude oil as it comes right out of the ground, just like we do with mineral oils. Now we do have the option, we can use natural gas hydrocarbons as well, but to be fair and honest, crude oil and natural gas, both are hydrocarbons, both naturally occur in the Earth's crust. One's just a liquid and the other one's a gas. After that, we send it to the refinery. Now here's where it gets a bit different. When you think of a mineral oil being refined, essentially we're starting with all sizes of hydrocarbon molecules. We don't want the smalls, we don't want the larges. We just want the mediums. Well, if you can keep that kind of t-shirt sizes in your mind here, when we make a synthetic oil, ultimately what we're looking at is we're not content with just the mediums. We want it even better. So what we do is we look at this cross section of mediums and we say there's such a thing as a small medium, a medium medium, and a large medium. And we really only want the mediums. We don't want the smalls and the larges in that medium range. So step two, when we refine it, we're just going to be a bit more thorough about the whole thing. We're going to get to a much narrower band of hydrocarbon molecules that we want. But after that, step three is exactly the same. We add some additives, in fact, very similar additives, and then we package it, of course, in near identical packaging. So this is what we need to understand, is just how different is step two. How different is the refining? And again, this is not a chemistry lesson, so we don't need to get into a lot of detail here, but we do need to understand why are they so different. So if you've ever seen a presentation about synthetic oils before, one of the most common graphics that people like to show you is one that probably looks like this. And this is very misleading. The intent is good. The execution is a bit off, though. What they're trying to show you is that with a mineral oil, you have, as I said, small mediums and large mediums, and you don't want those. But if you could have nothing but mediums, then you'd have a much more uniform compound here, and things might look a little bit better. So with this graphic, it seems to imply how smooth the layer of lubricant might be and how low a friction you can achieve. And the reason I say this is misleading is for those of you familiar with the Strybeck curve, so I'll throw up an example of the Strybeck curve here. Ultimately, when we talk about operating pieces of equipment, we're usually looking towards the middle of that Strybeck curve, somewhere after mixed lubrication in that regime of either EHD or HD lubrication, right? Elastohydrodynamic or hydrodynamic lubrication. That's where we want to be. This graphic showing you different size molecules between two surfaces really is actually addressing a very narrow band of the Strybeck curve right there. That's the only time a graphic like that would be true, is under extreme boundary lubrication. So either extraordinarily thin film applications like the nano device in your cell phone that can tell which way you're tipping it, or very heavily loaded or other similar applications. So for most of us, that graphic actually doesn't apply. So that's not a very good graphic in my mind, and that's why I don't try and use it to explain synthetics. Here's my preferred graphic that I think does a better job explaining why the molecule sizes being different is a problem. When you look at a mineral oil, and you do have some, and the term I use here is variability of the molecular sizes, you have some small molecules which are a bit more volatile, so they may evaporate off. You have some larger molecules which can affect your viscosity, but you also have a lot of impurities or at least a possibility of impurities in there. So with these varied molecule sizes, you don't get necessarily the best performance. And that's the whole point about a synthetic. With a synthetic having what I would call uniformity, all the molecules are much more similar in size, and therefore every molecule behaves the way you expect it to behave. So we don't have all the inherent problems that a mineral oil could have, not saying it does have, but it could have. We eliminate those right from step 2. The molecules that come out are a much narrower band. And I think the easiest way to picture this is just to look at a molecular weight distribution and just understand that they have the same molecules in them, right? The mediums are in both products. But what a synthetic oil has is it does not have anything other than mediums. A mineral oil, on the other hand, will have some of the small mediums and some of the large mediums, and that does affect performance and doesn't give us quite as good of a performance. So there it is in a nutshell. That's the simple side of explaining this. That's trying to just give you an overview of how oils are made and why there's a bit of a difference. Now, ultimately, as step 2 is done, as these refineries refine their products, before we go to step 3, before we add any additives, we have a classification system. And again, many folks have seen a variation of this, so this hopefully looks like something relatively familiar. But API has some criteria for how oils can be classified as a base oil. And there's 4 main ones we need to understand. And this table summarizes them quite nicely for us. So let's just go through the table, explain them a little bit as we are going along, and then summarize it all together. So talking about an API Group 1 oil, according to API, this is an oil that has less than 90% purity and or more than 300 ppm sulfur, and the VI is nothing special. Now, typically how these types of oils are made is through a solvent refining process. So this is basically that fractional distillation I was describing. It's an old technology. We've had it for about 150 years. We've been making oils this way for a long time. They're not necessarily the best oils. Technically speaking, this is what we'd call a mineral oil. When we go to a group 2, on the other hand, we're achieving over 90% purity, or we're having less than 300 ppm sulfur, but we have not affected the VI. So the viscosity index is about the same. It's not to say it's a superior product from that perspective, but definitely purity is one of the key ways we can differentiate this. And these are typically manufactured using a process that begins with the word hydro. So whether we call it hydro processing, hydro cracking, hydro isomerization, hydro refining, there's a variety of terms it can go under, but hydro is always at the beginning. It's always the prefix. And what this is hinting at is that when we separate out the smalls, the mediums, and the larges from each other, inevitably we end up with a bunch of carbon. And a hydrocarbon has to have hydrogens to it. So we inject high temperature, high pressure hydrogen into the mix, and we get a better yield, and we get more hydrocarbon molecules. So that's in the simplest statement, what is a big difference between solvent refined and hydro refined process, whatever word you want to use there. But a group 2 does have some benefits, some better performance to it. Where we get really interesting, though, is when we get to a group 3. We still maintain the over 90% purity or the less than 300 ppm sulfur, but now we actually have an improved viscosity index. So things start to look better from a performance perspective. And this is really an interesting category because you can get some very, very good oils out of a group 3. And in terms of purity, I mean, the target is 90%, but there's some water white clear base oils out there that are 99.9% pure. They're extraordinarily pure and they're made very, very well. And one of the key methods of manufacturing that exists out there is referred to within industry as catalytic dewaxing. And it's just this extra step along the way when you're doing your separation after it goes through fractional distillation to get the smalls and the larges mostly out of the oil. We can use this extra step here to really try and refine it and narrow that band of what the mediums look like. But essentially, API groups 1, 2, and 3, from a technical perspective, are still all just mineral oils. Where we get into the curious side of synthetics is once we start discussing this group 4. Now, as you can read through the criteria, they don't give us a listing of purity, sulfur content, or VI because they don't need to. Any oil that's made as a PAO or polyalpha olefin, this is an oil that is automatically qualified as a group 4. And this is essentially 100% pure, no sulfur, and just an awesome VI. If you look at the way it's manufactured, and this is a new word for many people, oligomerization. So we'll talk about that in a little bit. But for now, understand it is not separating out the smalls and larges from the mediums. Oligomerization is a way of using the smalls to make more mediums, but we'll get into a bit more detail in a second. This, technically speaking, is a synthetic. And this is where the discussion has to travel back in time a little more than 20 years ago and just refer to a story maybe some of you have heard countless times, but for those of you who hadn't, there was an issue here. And this is where we had a differentiation between the technical term for synthetic and the marketing term for synthetic. And this arose because of a dispute caused by Castrol and Mobil's basically disagreeing with some things that were going on between the two. So as you can see here, Castrol used to manufacture their Syntec product line using PAOs. So it had been a PAO. But in the late 90s, they had switched away from PAO and they went to essentially a really good quality hydroisomerized base stock. And hey, everyone can make their own decisions, everyone can change what they're doing, but Mobil took offense to this because when Castrol marketed this new version of Syntec, they made at least a couple of claims that kind of, ruffle the feathers over there. So one of the claims was superior engine protection. But the other claim, and this is why we went through a little bit of the details that we went through, unique molecular bonding. Now, again, I didn't make this a chemistry lesson. I didn't want it to be a chemistry lesson, but I tried to give you enough of a background so that you'd be able to look at that particular statement and make your own critical judgment on that and go, wait a minute. There hasn't been anything I've described so far that would indicate the molecules in synthetic oil, a PAO, would be any different than the molecules in a group 3, by and large. So you should already be doubting that statement right there. So as the story goes, Mobil went and complained to the National Advertising Division, so the NAD, and they said, hey, these claims are unsubstantiated, they're just not true. They also claimed that because Castrol went away from a PAO, that they had degraded their lubricant, that it wasn't as good anymore. And this was really kind of the basis of their complaint. So the NAD looked into this and said, fine, we'll pass a judgment on this, and they did. So when they made their decision, the NAD basically broke it into these 3 statements. Was their reformulated Syntec still a synthetic? Did they have any substantiation to these claims that it provided superior engine protection or anything like that? And did Mobil have a case that the Syntec was a degraded product compared to its original formulation? So the second question was easy to answer. No, Castrol had not made any studies to prove that their oil was really better. So that was an easy one for an NAD to come to a conclusion on. Same with the third question. It hadn't been provided a sufficient evidence by Mobil to suggest that it was a degraded product. So those 2 decisions were easy. But herein lies the problem. Was the reformulated Syntec still worthy of the term synthetic? And part of this whole discussion, why I'm saying long story short here, is that the SAE and API have both removed from their documents definitions regarding what a synthetic oil was or was not. So it came to the NAD, which is basically not a technical body, but a marketing body, to come up with a suitable definition or allowance of the use of a term. And ultimately, and this is why I say, well, they allowed Castrol to go forward with this new product and be able to call it a synthetic. So in today's world, most of us recognize a group 1 or 2 base oil absolutely as a mineral oil. We all agree a group 4, absolutely a synthetic oil. Group 3, on the other hand, maybe it is, maybe it isn't. It kind of depends who's making it and how it was made and what sort of qualities it hits. But we do allow many group 3s to be marketed as a synthetic, whereas some other group 3s are simply marketed as mineral oils. So that clear-cut black-white definition that we used to have in the API base oil categories hasn't really been around since about the 90s when some of this stuff started happening. So for the last 20 years, we've had the term synthetic thrown around a little bit in ways that, generally speaking, only because of the lack of a definition or the looseness in the use of the term has allowed the word synthetic to be applied to a lot of other things. Now, as I said when I showed you the API classification tables, there were 4 categories we needed to know. You probably noticed there was 5 in the list here, because API Group 5 doesn't have any qualifications for purity, sulfur content, VI, none of that. Group 5 is what we call a catch-all category. Anything that does not fit the description of a 1, 2, 3, or 4 for whatever reason. Maybe it's a purity issue, maybe it's a sulfur content issue, maybe it's a VI issue, whatever it is. If it doesn't fit the first 4, it's automatically called a 5. And the problem with that in terms of my presentation is that many, many other synthetic oils are group 5s. So when we think of things like polyol esters and phosphate esters and some of those products, which most of us would agree are synthetic, those are group 5s. But one of the other ones that's a group 5 simply because it doesn't fit well in any of the other 4 categories is a naphthenic-based stock, similar to what we would use in, as an example, refrigeration compressor oils. So it's very much a straight up hydrocarbon oil. It's made using fractional distillation by and large. It doesn't seem like it should be called synthetic, but it can't be called a 1, 2, 3, or 4, so it falls under group 5. Because group 5 contains so many other synthetics, people sometimes mistakenly assume that all 5s are synthetic and therefore naphthenic-based stock must be synthetic. So this helps you understand, maybe doesn't make it clear, probably muddies the waters a little bit, but with the API classification system, it's very clear where oils fit, but it's not so clear what is or is not a synthetic. Definitely, like I said, we agree 4 is synthetic. 3, maybe it is, maybe it isn't. 5, again, some are, some aren't. 1 and 2, by and large, you're probably seeing marketed, labeled as a mineral oil. Now, it's not to say somebody doesn't make a really, really good group 2, and it looks almost like a synthetic, but it's that VI difference that really differentiates 2 versus 3. And just to give you an idea of where we've come in the last half a dozen years, this is the global output by API base oil type. And you'll notice that we haven't really changed how much group 4 and 5 we're making, but we've made incremental increases in how much group 3 is available out there. But the big shift has been we've made less 1s and more 2s. So you can see that really 2s and 3s have been gaining popularity, 2 more so than 3. And 1 is the one that's losing out. We haven't really increased output on the PAOs or some of the other stuff. And a lot of people wonder, well, why is that? Why are we making more 2s and 3s? Why do we drop 1s? I can kind of summarize it this way. Basically, yes, it's cheaper to make a 2 and 3 versus a 1. You can start with a lower quality crude, and generally speaking, you get higher performance, better VI, stuff like that. So essentially, if you can start worse and better and make more money while you're doing it, why wouldn't you? So many companies have invested in upgrading their facilities or mothballing some of their older ones and shifting production over to 2s and 3s. it hasn't been because of consumer demand. We take whatever is given to us. Some products we sometimes prefer that they stay as group ones, but more twos and threes are available. So to summarize everything we've talked about at the moment, let's just go through a quick list of definitions. Essentially, the term mineral oil applies to any oil that's made by a physical separation, usually distillation, like I said, as I described in the beginning. We separate the smalls and larges away from the mediums. When we use the term synthetic, and you notice I got little air quotes around synthetic, the way I paraphrase that is it's significantly modified, chemically different. We have altered the chemical structure somehow. And the word often we use for that is synthesis, and that's why synthetic fits the term here. But like I said, you can do this using group 3 technology. You can do it with group 4 technology, and there's even some 5s up there that qualify under the term synthetic. For those that are curious, though, when we say re-refined versus recycled, these are two terms that get thrown around sometimes, and they're a bit confusing because when you hear the term re-refined, you know that the oil had to go back to the refinery and it was refined again. That seems like a pretty straightforward definition. But when you recycle something, how do you recycle it? Well, funnily enough, the way some oils get recycled is they get sent back to the refinery. And so people go, well, if it's recycled and it goes back to the refinery, does it become re-refined? Or if it's been re-refined and it gets reused, does that make it recycled? How do you know when to call which one which? And essentially, the distinction I make that helps me understand which way the terms go is if you reuse the oil in its original form, meaning that you've collected used engine oil from all the quickie lubes, send it back to the refinery, and they make you new engine oil from it, that would be a re-refined product. But if we collect oil from any source and we send it to the refinery, and what the refinery coughs out is not a lubricant, but something more like fuel, that's a pretty common one, we've changed the secondary use of the product. We're not reusing it as it was originally created. That is a recycled product, right? And the analogy I often use is when you go shopping for a layer of clothing to wear when you're hiking, you might buy a fleece as an example, fleece leggings or a fleece coat or fleece vest. Well, a lot of that fleece is recycled pop bottles. Right? It's the same plastic that goes into making pop bottles and goes into making fleece. And one of the cheaper ways to make fleece is to collect these pop bottles and then turn them into the fleece. So fleece is a recycled form of a plastic pop bottle. But if you deal with glass ones, well, glass ones can get washed and reused. That's reused as its original purpose. But those definitions just give us a quick, like I said, summary of what we've talked about so far. But I think to try and hammer this point home to make sure we're all on the same page here, I came up with an analogy. So my analogy is to compare everything I just zipped over here regarding the petroleum industry and compare it to the dairy industry. So with the petroleum industry, I said step one was we got to get crude oil out of the ground, right? So that is where the raw product is located and how we deal with it. It's a naturally occurring product. We extract it, we bring it to the surface, we do something with it. So what's the oldest technology we have for dealing with crude oil? That is your group 1 solvent distillation. How do we do it a little bit better? That's where you hear the term hydro, because we're injecting high temperature, high pressure hydrogen. Now, when we go to group 3, the big difference here is we're actually getting an improvement on the VI. And last but not least, that fun new word that we learned, oligomerization, was what we have when we created group 4. So that is a quick overview, like I said, what I've already talked about, but let's now draw the analogy to the dairy industry. So where does the raw product in the dairy industry come from? Well, that's easy. That's milk out of the cow. We can agree that crude oil is a naturally occurring product. We can agree the cow naturally makes milk. Thing is, crude oil doesn't come out of the ground on its own, and the cow cannot milk itself. It takes our intervention to get these products to the next stage. Now, what is the oldest technology we have for separating milk from cream? That's easy, right? Cavemen would have done it this way. It is gravity. We just let the milk sit. Cream rises to the top. We can skim the cream off. We're left with the milk. Now, how would we do this better, faster? Well, if you remember pioneers had something we called a separator. And a separator would basically spin it, centrifuge it, and we get better separation and faster separation. So the purity of the milk was a little bit better, the purity of the cream was a little bit better. So that's kind of holding up with our analogy. Now, we don't care about the VI of a milk product, but what we might care about is the shelf life of a VI product. So how do we do that? Well, we can hit it with a high temperature for, oh, my slides keep doing that, with a hit it at a high temperature for a brief period of time. And this is long enough to kill the bacteria, but not long enough to curdle the milk. And we call that process pasteurization. So I'll admit, it's a weak analogy at this point. It doesn't really work very well. But how do we make a milk product by modifying its molecular sizes? How do we oligomerize milk and make a synthetic milk product? And sadly, because my slides have jumped around, you've probably seen the answer here, but for those of you who weren't paying enough attention to catch it, try and think of this. What is a milk product made from milk straight from the cow with no other ingredients? So cheese needs salt, yogurt needs bacteria, and things like ice cream, of course, needs sweeteners and flavors added to it. Well, about the only other product you can really think of in the dairy case that doesn't involve extra ingredients is butter. Butter is absolutely synthetic milk. How do I know this? Well, unless you can show me which teat on a cow produces butter, I'm not going to believe it's natural, right? The cow can't make butter. It takes us. We need to make the butter. So how do we make the butter? It's because we force little fat molecules into being bigger fat molecules, and we get ourselves butter. So let's talk about this side of the analogy. Let's truly understand what I mean by converting milk into butter. So here's a fun experiment. If you've got kids, this is great, especially now that we're all locked up, trying to stay at home. Search through your cupboards, find yourself a mason jar. Now, with this mason jar, you're going to need one other ingredient to make this scientific experiment go well. Go to your local dairy and buy milk straight from the cow. Now, that's a great piece of advice if we're allowed out of the house. So best second option we have, when you're next at your grocery store or getting groceries delivered, buy some whipping cream. Get yourself some whipping cream, pour it inside the mason jar, seal the mason jar. Now, hand it to the child and tell them to start shaking it. So what's the first thing a child makes when they start shaking up a mason jar full of whipping cream? Well, that should be a pretty easy answer. They make whipped cream. However, tell them to keep shaking it. So they keep shaking and shaking and shaking this mason jar. It takes about 2-3 minutes. But if they keep shaking it, even though it's full of whipped cream, if they keep shaking it, they will then start to hear and feel a bit of a thump in there. And if they shake it for about 3 to 5 minutes, in the end, you will get kind of what you see in the picture here. There will be a definite lump of something inside the mason jar. So what we end up with, essentially, if you separate them, is the lump and a bunch of leftover liquid. Now, if you look at the lump is the butter, and that's pretty tasty homemade butter. You might want to add some salt to it, but other than that, it's pretty good stuff. What are you left over with, though? I know this is, when I do this in groups, there's always a fun question to see if anyone in the group can name what that liquid is called, because a lot of people start guessing, you know, whey and other terms, and really all I'm looking for is the term is buttermilk. It's not a difficult term to remember here. When you make butter, the leftover liquid is called buttermilk. And you'll notice it's usually a lighter color and definitely a lower viscosity than the whipping cream that you started with. But here's the thing. If we take that buttermilk and that lump of butter and we decide to throw it in a blender and we blend it back up, what we're going to notice, we can't go back. It will not return into being milk and cream. So in our experiment, we started with one liquid. We shook it and we shook it and we shook it, and we ended up with a solid and a liquid. That sounds pretty significantly modified to me. But the fact is that we can't go back. We can't take the liquid and the solid and put them back together. That is definitely now chemically modified. So if it's been modified in such a way that is different, chemically speaking, we can define this as synthesized. Butter is synthesized milk. Now, we didn't create milk from something else. We just took the molecules that are normally in milk and made them into something different. And that is, I think, the best way to try and explain what this term synthetic really means, because how did the butter get made? Well, you may or may not know this about milk, but milk is what we call a colloidal mixture. It has water as a base, and it has particles suspended in it, not dissolved in it, right? When you put sugar in water, that's a solution, right? That is dissolved solution of sugar into the water. Milk, on the other hand, has fat molecules in it, and the fat is not dissolved into the water. The fat is suspended in the water. So when you shake that milk up inside the mason jar, you're slapping together all these tiny little fat molecules, and they become bigger fat molecules because they start bonding with each other. And if you keep doing this over and over and over again, the slightly bigger fat molecules will bump into the other slightly bigger fat molecules, and they'll form even bigger fat molecules to the point they become very, very large and are the desirable size for us to call it butter. The term oligomerization that I used to describe group 4s is exactly that process. Now, it's not done in the mason jar, I'll give you that, but it is taking smaller molecules, monomers, and pushing them together, chemically speaking, to become larger. So we're taking small molecules and making them into medium molecules. Now, we're not going so far as to make them into large because we don't want large, we just want medium. But that, to me, is one of the easiest ways to understand what do we mean by synthetic. We start with 100% natural ingredients. I sound like a commercial for something now, but we start with 100% natural hydrocarbon molecules, and we basically force fit them to being the molecule sizes that we want, the mediums. And like I said, we're not just content with mediums, we want mediums. So we force them into this very narrow band, this very narrow size range of hydrocarbon molecules without the impurities, without the other issues, and we end up with a synthesized lubricant. It didn't occur naturally. We wouldn't have come across it on our own. It did get made, by man, so it's arguably man-made. But like I said, so many people, when they picture man-made, assume that it had to come from something else. So butter is synthetic milk. Is the easiest way, like I said, to understand what the word synthetic means. Now, just to wrap up our discussion here on synthesized products, when you look at the synthetic oils that are available in the world, PAO, that group 4, is among the most common by volume. The other group 5s that you see filling up the rest of this pie, they make up smaller slices. And this is a bit deceiving because when it comes to using synthetic lubricants, applications where you might use, say, a phosphate ester or another type of ester like a polyol ester might be an application that is actually substantially larger than the applications where you use PAOs, like talking about sump volumes or reservoir volumes. But the thing about phosphate esters and polyol esters is you can get years and years worth of service, even decades worth of service out of these oils. Whereas PAOs, still mostly based on contamination, end up in applications whereby the oil drain interval is much shorter. So even though we might have, a 6,000 gallon reservoir filled with phosphate ester compared to a, 1 gallon reservoir of, passenger car motor oil, there's a lot more cars on the road than there are phosphate ester systems, and we change oil much more frequently in a PAO application than we would in a phosphate ester application. So that's kind of why these slices of the pie are a bit misleading, but PAO is definitely the most common of the synthetics by volume, and the other one's significantly smaller. So to help us understand all these, I quickly will run through basically the advantages, disadvantages comparison. So from mineral oil, it's got low cost. That's really one of its best benefits going for it. The disadvantages, because we have that variability of molecular size, we don't get the thermal stability, we don't get the oxidative stability. We gain this when we go to a PAO. We have much better oxidative stability, we have much better volatility, all those kinds of good things. The big disadvantage, costs more, right? So there's a trade-off here. But with some of the other synthetics, we start to see different advantages and disadvantages. With an ester, whether it's a diester or polyol ester, we do get definitely better oxidative stability, handles high temperatures very, very well. Generally has fairly reasonable VI, good at preventing sludge formation. Generally, it's fairly compatible with other mineral oils and synthetics. Downside is it hates water. You get water in it and it will degrade much quicker than some of the other products out there. Does not handle water very well. Another issue is it doesn't play well with certain seal materials and coatings like paints. So we can't just necessarily switch over a system to an ester without having made some compromises or some changes to the system. When you look at the PAGs, the polyalkylene glycols, they are very, very good at handling the high temperatures, have an even better viscosity index, pretty good for the low end too in terms of pour point. They have a lot of good things going for them. They do have a few problems though. Generally speaking, they will absorb a bit more water. They will not play well with mineral oils if you happen to have some cross-contamination. Now this is mitigated. There are some variations of PAGs out there called OSPs, oil-soluble PAGs that don't have that issue, but generally speaking, just grouping them together, being a bit stereotypical application of a PAG, they don't always play well with mineral oils. But the other issue is much like the esters, they don't play well necessarily with different seal materials and coatings, and they may have some issues with other products. Right? Group 5s are relatively well known for not playing well with group 1, 2, 3, and 4, whereas 1, 2, 3, and 4 generally play well with each other. When it comes to the phosphate esters, these ones have the best fire resistance amongst all products. They're very thermally stable for the high temperatures. They're actually pretty decent hydraulic fluids with some natural, meaning non-additized anti-wear properties. So a lot of positive things going for them. You go, ooh, geez, why wouldn't we just use these everywhere? Well, they're one of the most expensive products you'll ever come across. They don't handle temperature swings very well in terms of VI. They really don't play well with seal materials and coatings. I mean, they're an excellent paint stripper if you ever use it. And again, it's one of these products that does not play well with water. You need to keep it very, very dry to have long-term performance out of it. The alkyl-benzenes, which is a product line that gets used in a lot of compressor applications, it has some fairly good positives. It doesn't really stand out as the top performer in many ways, but it does have a very good pour point, which makes it an awesome choice for refrigeration compressors. It tends to be very low cost as well, relatively speaking. So it's got those positives going for it, but it doesn't handle the temperature swings from a VI perspective as well as some of the other products can. And again, doesn't always play well with seal materials. So as you can see here, if you switch from one base oil to another base oil, whether or not they're compatible with each other is part of the issue, but whether or not they're compatible with the existing systems, seals, and coatings is always a concern. The last one, though, here is silicon. And silicon, being completely different chemistry here, has an awesome VI. It's almost double what any other product would be in terms of VI. It's fairly good at handling high temperatures. It handles water reasonably well. There's a lot of things going for this. Downside, much like phosphate esters, it's one of the most expensive products you're ever going to come across. It's actually a terrible lubricant when it comes to very thin film applications. Does not play well with other hydrocarbons. And worst of all things is if you end up actually overheating it, it can form a lethal gas. So it's definitely got a safety issue related to it under extraordinarily high temperature applications. But as a general heat transfer fluid, it's an excellent fluid. That way, it's just not really what you generally use as a lubricant. So keeping all these in mind, I threw in one extra slide because I often get questions related to this, and this is sort of outside our hydrocarbon synthetic versus non-synthetic discussion, but just people, knowing these advantages and disadvantages, usually ask me about vegetable oils. So vegetable oils being a completely different entity here. The big advantages with vegetable oils is their toxicity and biodegradability. That's sort of the key thing that makes them desirable for certain applications. It's great for using in places where you're worried about contact with the environment. Downside is they don't necessarily handle as high temperatures as a lot of the hydrocarbon-based products. We do have limited availability of the products, so that tends to drive the price up a bit. We also don't have as much ability to add all the same additives. So you're seeing that there's very few vegetable-based products out there compared to how many hydrocarbon-based products are out there. But each their own, right? Every oil's got its place, and that's kind of the last thing I wanted to leave us on, was just to show you a bit of a summary, got out of a textbook here. But if you try and compare some of the more common oil types that exist out there, mineral oil is essentially kind of a middle of the road answer. It is not going to be the best at everything. It's very good at what it can do. It's just limited in how far it can do that. So PAOs, generally speaking, again, like I said, they tend to be among the more popular. They tend to do everything a mineral oil can do, but a little bit better. And the balance is they're not among the most expensive products out there, so you tend to be able to justify a cost increase if you can see the performance benefits. Some of the esters that exist out there, they do have properties that are even better than the PAO, but there's generally a trade-off somewhere along the line. And VI is a very common one. That's why we don't see esters in all applications, because when you have wide temperature swings from start to operating conditions, they're not as good that way. And some esters may not be as good at handling the higher temperatures as others. Now, PAGs are certainly popular in some applications, and they do handle those two particular properties, VI and oxidation stability, better than the esters, but then they have trade-offs themselves with some of the other things. And most notably, like I said, collectively, PAGs are not known for having mineral oil compatibility, but there is such a variant of a PAG called an OSB, which is excellent at doing that. And then silicons, like I said, silicons have among the best VI of any oil. That's extraordinarily high, but they're just not good lubricants. So when it comes to selecting oils, right, we always have to decide what is the main property or properties that we're going for, and decide what properties might we be willing to make a bit of a sacrifice on or have no requirement for. And that's what can help us decide if we're willing to move away from a mineral oil, go into one of these synthetics, whether it's a group 4 PAO synthetic or it's one of the group 5s that qualifies as the name synthetic. But ultimately, at the end of the day, I'm hoping what you got out of this presentation was an understanding that synthetic does not mean man-made, as in it came from absolutely laboratory-created molecules. It just means we manipulated what was already there into something that wouldn't naturally occur. And the most common form of this is a PAO. That is the most common form that most of us have, either used or are aware of. Mobil and Chevron are among the largest suppliers of PAOs here in North America. Castrol is one of the largest suppliers over in Europe. But ultimately, there are other oils that get called synthetic as well, and those come from even more companies. And like I said, they tend to be from more specialty applications, in particular fire-resistant fluids or compressor-type fluids, very specialized formulations for those. So that's essentially all I had to go through. I'd like to turn it over back to Heather to see if there are any questions that have come up. If you do have a question, there is a question feature on your GoToWebinar tool, or you can, of course, also use the chat. I would see that immediately, but if there's any questions now, I'll let Heather take it over again.
Yeah, no, thank you very much, Evan. That was great. So it looks like the only question that I have received is that sometimes I see with the oils that they have a group 3 plus. What is different about the plus, and are there other groups that have the plus as well?
So 2 and 3 are known for having a plus, and these are not real, and the keyword I might use is legitimate classifications. They're not endorsed by API as part of their API 1509. Appendix E is where you get all these criteria from. So there is 1, 2, 3, 4, and 5. Those are the only recognized ones. When people market it, and again, this is where we get into marketing terms versus technical terms. Plus tends to be something where they're just trying to differentiate themselves and say, we're a little bit better, right? We don't make it so good, we call it a 3, so let's call it a 2 plus. And they're like, we make a really good group 3, but we don't make it through oligomerization, so it can't be called a group 4, it's not a PAO, so let's call it a group 3 plus. Just marketing terms. Yeah, they're not real. There's no really usage outside 2s and 3s. I can't say as I've ever seen people market a 1, 4, or 5 with a plus symbol, but I would just like to see nobody use a plus symbol because it's misleading.
Oh, I understand. Otherwise, I don't see any chats or questions coming through. But if anyone does have questions, you can see Evan's email address there on this last slide. So feel free to email him if you have a specific question that you'd like to discuss with him one-to-one. Otherwise, you can always go to www.testoil.com for more information as well. And otherwise, I want to thank everyone for joining us today. And I hope everyone stays safe, stay home, stay healthy, and take care. Thank you, Evan.
All right, thank you, Heather.